The guitar string constitutes a standing wave, and the amplitude for a standing wave is twice the amplitude of either the incident or reflected wave amplitude. So this is going to be 2 times the amplitude of 7.5 times 10 to the -4 meters, which is going to give us a standing wave of 1.5 times 10 to the -3 meters. The angular frequency for this standing wave is 2 pi times f, which is 2 pi radians times 440 hertz. So we get a angular frequency is 2760 radians per second. And then the wave number k is given by omega over v, and that's 2760 radians per second divided by its velocity, which is 143 meters per second, which gives us a wave number of 19.3 radians per meter. And now if we use the general equation for a standing wave, which is the amplitude of the standing wave times sine kx sine omega t, we can say that this is 1.5 times 10 to the -3 meters sine of 19.3 radians per meter x times sine of 2760 radians per second times t. For part B, we're asked to find the nodes, and we know that the nodes occur at multiples of half a wavelength. So we have at x equals 0, lambda over 2, lambda, 3 lambda over 2, and so on. And we know that lambda is equal to the velocity over the frequency, which is 143 meters per second divided by 440 hertz, which gives us a wavelength of 0.325 meters. So we can say that the nodes are going to be at x equals 0, x equals lambda over 2, which is 0.163 meter, lambda itself is 0.325 meter, 3 lambda over 2, which is 0.488 meter, and so on. For part C, find the amplitude of the standing wave and the maximum transverse velocity and acceleration. So we already know that the amplitude of the standing wave is 1.5 times 10 to the -3 meters, which is 1.5 millimeters. This amplitude occurs at the antinodes, so the opposite location of where the nodes happen, and those opposite locations would be midway between the nodes. So that would be at antinodes would have a location of, instead of between lambda and lambda over 2, would be lambda over 4, and so on. So we would get at x equals lambda over 4 would give us excuse me, 0.081 meters. The next one would be at x equals 0.244 meters, and the next one would be at 0.406 meters, and so on. The velocity is given as the derivative of the y function with respect to time. We use partial differentiation here, so this is going to give us 1.5 times 10 to the minus 3 meters times the sine of 19.3 radians per meter x times the derivative of the time-dependent sine portion, which is going to be cosine of 2760 radians per second times t, and then times the derivative inside of the argument, which is 2760 radians per second. And that will simplify to about 4.15 meters per second sine 19.3 radians per meter. I should have said meter, not seconds on the top. X cosine 2760 radians per second times t. For acceleration, we take the time derivative of velocity following the same steps we did above. We would get a function of negative 1.15 times 10 to the 4th meters per second squared sine of 19.3 radians per meter x times sine 2760 radians per second times t. The anecdotes of the velocity. So for v of x of t, we have antinodes at locations where the sine of 19.3 radians per meter x equal plus or minus 1, and we know that it's going to vary in amplitude between plus and minus 4.15 meters per second. That's the maximum velocity. And then for the acceleration function, it has antinodes at the same location as above, and the acceleration is going to vary between 1.15 10 to the 4th meters per second squared, positive and negative.